Assalamu alaikum warahmatullahi wabarakatuh. Welcome you in our next chapter, that is 12.8. So you have already done this one in earlier course of your calculus 1. There we discussed extrema of the function, but the function was one variable, was y equal to f of x. As we have here in this picture, the function is y equal to f of x, and we have the graph of the picture for that one. At the point where the extreme value, then we say there the derivative f dash of x is equal to 0, or we say f dash of x does not exist. There are 2 points. We say here this x over c, f dash of c equal to 0 instead of f of x. We can just replace x by c, and then we put a condition on c that c is in the domain of the function. If it's not in the domain of the function, then we don't discuss it. If the domain of the function, then say c is our critical point. So we get the critical points in our domain of the function, and by finding the derivative and putting that equal to 0, and then to discuss the maximum minima, we use first derivative test and second derivative test. Here I'm going to discuss second derivative test. Find the second derivative of the function, and we find the value of the second derivative at point C. If this value is bigger than 0, we say there is a local minima at that point. And we say f double dash of c, f double dash c is less than 0, we say at that point we have the local maxima. So that's how we can find the local maxima and local minima. And this test we say second derivative test. We are doing the same thing in case of the several variable. We're just going to extend this idea to the function of second variable. If we have the function of two variables, we say where z is the function of fxy. So we have the variable x and y as independent variable, and z is a dependent variable. So we are going to extend the same concept for two variables, and we have the function z is the function of x and y, where x and y are independent variable and z is dependent variable. This means z is changing with x and y, and we want to discuss the derivative. We say we having a gradient which contains derivatives x and y. So we have already discussed this. We say this application of the gradient. So we say we having the critical point because it's a function of two variables. So the function of one variable we get a point, we get a number, but two variable we get a point. They will get the value, the coordinate of x and coordinate of y. That's the point. So we say we will get the point. So the gradient, we say the gradient of the function is equal to 0. I say gradient of the function f xy is equal to 0. That's equivalent to the first derivative. We say equivalent of this one is equal to 0. That means if I extend this one, this is my gradient of fxy is f of x and f of y, and it's a vector 0. Vector 0 has two coordinates 0 and 0. So that give me here, when these two vectors are equal, the components are equal, we get here f of x xy is equal to 0 and f of y xy equal to 0. So we get the critical points by solving this equation that f of xy, the derivative with respect to x equal to 0 and with respect to y is equal to 0. And then as we said before that we say it does not exist when the derivative does not exist. Say if this is here this is equal to 0, or we say the derivative f of x and derivative f of y does not exist. So at these points we say the critical points. So can I write the definition of the critical points? We say our critical points are the points we have the function here, let fxy, we having the continuous and continuous derivative, have continuous partial second derivative, partial second derivatives. When I say second derivative means the first derivative are always there exist, second partial derivatives. A point AB is a critical point is of f of x AB as I defined above is equal to 0, and f of y AB is equal to 0. Or we have the second one, or we say number 2, that is the second condition that we get here. This has the critical point, or number 2, these partial derivatives f of x AB and or f of y AB are here, or f of y AB does not exist. So these points we say they are critical points, and on these critical points we are going to discuss at these points we will discuss the maximum minima as we have discussed at the critical numbers. So the first was the critical number, and then we take our test and we defined our values. So we defined the maximum minima. So as we are doing there also partial derivative, second partial derivative. Similarly, we are going to use also a second partial derivative to find to discuss the local extrema of the function. So I'm just going to explain you with the help of this figure. We having here this surface z of xy, and this is our xyz plane, and this region R contains the points. These are the points we are having the maximum minima. So the highest point is a maxima, and this point is a minima. So we can have, if it's the absolute, that means the maximum, the largest one, in reference to other points, we say that's the absolute minima and absolute minima. Otherwise, we say relative when we are just taking the neighborhood, and we say the largest value is at this point, we say it's a local. So this here we can find here, you can see it here in three dimensions, how we can discuss it. And here we are having the surface, and this is relative maxima. So this point x0, y0 is point value here on the surface is x0, y0, 0. This highest from the all other points, so this is a local maxima, and this is here is dip, and we are having this one is the relative minima, and this is relative maxima. So here we can have the also the picture, in this picture we can have the local maxima and local minima. So in this picture we have 1, 2, 3 points, these are critical points, and these 2 points are the high points, and we say in this one we are having the value, this is local maxima, and this is also local maxima, is local minima. We want to say the absolute maximum, so this point will give me absolute maxima, and this point will give me absolute minimum. So this is the idea we're having about the local maxima and local minima. And as I discussed the idea of the critical point, so this is a point is a critical point as point AB. So here we can see this surface, and we are having this derivative respect to x partial derivative, y is constant, here partial derivative x is constant. This is a point on the surface where they are equal to 0, and this point becomes the critical point. So this is the idea behind this one. We come back and we discuss it further here with the help of example. We'll use secondary test for finding the extrema of the function of two variables, and there is a two part of that one, because when we say secondary test, it means we are having here the derivative f of xx, f of yy, and f of xy. So we need here identity which combine all this one, and this is known as discriminant of this function of function f. We denote this discriminant by dxy, and the definition of this discriminant is that we combine these as a determinant. We have f of xx, f of xy, f of xy, and f of yy. When you open this determinant, then we get here f of xx and f of yy minus f of xy whole square. So this is my discriminant, and my values, that will depending on if I just write it in the function of xy, that's much better. So for understanding purpose, that we are having this function of xy, and then we put the value of xy and we get the values. Here my f of xx, the function of xy, and f of yy, the function of xy, minus f of xy, also function of xy, whole square. So once we find the critical points and this discriminant, this I take as number 1, and this is my equation 1. Then I find here the value of the discriminant at the point AB. AB is my critical point. At the point AB, find the value, and this value is less than 0. Then we say there is a saddle point. The saddle point is a point where there is no maxima, no minima. This point is like this one. From one is coming down, the other side is going up. At the one side, here we see this maxima, and here minima, and here maxima. So this point is saddle point. This is like a saddle. We put on a camel or we put on a horse to ride on that one. We have structure like this one and structure like this one. So that point says saddle point. So this is our saddle point. This is number 1. Number 2, we find the discriminant at the point AB, and this is bigger than 0. So at this point there is extrema. This can be maxima and this can be minima. And number 3 is where the saddle point D, AB equal to 0, then we say test fails. This test does not give us any information about the maxima and minima. So we don't have anything in this case.